We've been talking about examples of networks in many different domains and how networks are really pervasive in a lot of different applications in science and in society and in everyday life. And so now it's useful to talk about them further to begin delving into the mathematical definitions around them. So to start out, if we want to talk about networks, then we need the language of graph theory, the study of how things are connected and what those connections imply. So a graph is simply the mathematical term for the object that represents a network. A graph consists of two things: a set of nodes, which are the objects that we're going to connect, and then the edges, which are things that connect certain pairs of nodes. So for example, in a social network, the people could be the nodes, right? Those are the things being connected in the social network. And then the friendships are the edges. So if two people are friends, we say there's an edge between them. Right? So certain things in a graph have edges, and connecting them and certain other things don't. To make this more concrete, let's try drawing an example. And let's pick something that's actually small enough and sort of self-contained so we can actually look at it and play around with it. So this won't be a social network. This will actually be a physical communication network. It's actually the internet from late 1970. So the internet was quite young in late 1970, and it's a bit smaller. It was a bit smaller back then than it is today. In particular, it actually only had 13 nodes. Right? So the internet in late 1970 was architected as basically sort of these two rings. There was an East Coast ring with 6 nodes. It had sort of a mix of research universities and government-funded labs. So it had, on the East Coast, there was MIT, there was Harvard, there was Case Western, there was Carnegie Tech, which later became Carnegie Mellon, and there were these labs, BBN and Lincoln Labs. And the West Coast was a similar mix of labs and research universities. There was Stanford, UC Santa Barbara, UCLA, and Utah, and then labs drawn here as SRI, SDC, and RAND. Okay, 13 nodes, and that's all there was. And there were edges. There were edges between certain pairs of them. So for example, you see here that MIT was connected to BBN, Harvard was connected to BBN. Those are relatively local links. And then there were these very long-range links, MIT out to Utah, BBN out to RAND, that crossed much of the country. And these links were actually, in a sense, physical objects. I mean, when you put a packet in at MIT and it had to get to Utah, it actually went down physical cable and came out the other side of the computer that was at Utah. Right? So these were, at some level, computers wired together with physical infrastructure. Taking advantage of course, all sorts of other complicated infrastructure, right? Other national communication networks like the phone system, which existed at the time, but definitely sort of a network in and of itself with these 13 nodes. And when you look at it, you can sort of appreciate kind of some of the connectivity and this idea that there were these two rings and they had these two long-haul links. And that all kind of comes through when you draw the picture of the 13-node internet in 1970. One thing that also is important to appreciate is when you draw a network or you draw a graph like this, all that matters is what's connected to what. It doesn't matter where I put the nodes. In particular, they're drawn here purely to sort of look good, you know, to kind of be conceptually clear, but I could have drawn them some other way. And in particular, for example, although the East Coast and West Coast rings are suggestive, if you think about the geography of the United States, this is not actually how they're laid out on a map. So for example, the East Coast ring, you would actually have to kind of fold over to put Case and Carnegie to the west of MIT, BBN, Harvard. Okay, so really what matters is the connectivity. Now, what I want to do here is talk a little bit about some of the basic definitions around graphs, and we can illustrate these definitions with the graph that we have here. And I'm going to run through 4 or 5 definitions, and they're going to be sort of the bedrock of what we're going to be talking about, the sort of the language we're going to use when we think about graphs. Maybe the most basic definition that we're going to use is the idea of a path, right? So when I look at a network, the obvious question that you should ask yourself is, how do I get from point A to point B? If it's a communication network or a transportation network, that's sort of the question that comes to mind. The internet was there to send data from a computer at one place to a computer at another place. And so, for example, if I wanted to get from the internet node at Lincoln Labs to the one at RAND, I could say, how should I get there in a sequence of hops, right? So a packet at Lincoln could go, for example, through MIT, then on to Utah, through SDC, and down to RAND, and that would be a 4-step path that would get me there. We'll say that a graph is connected if there's a path between each pair of nodes. And certainly if you have a communication network, the goal would be for it to be connected. You want to be able to get from anywhere to anywhere. And we'll also talk about the lengths of paths, right? Some paths might be better than others because they're shorter, for example. And so if number of hops is kind of our objective, the thing we're really seeking to to improve. Then, for example, if we were to go from Lincoln Labs to Rand via MIT, Utah, SDC, so that's 4 edges, we'll say that that's a path of length 4. Right? The length will be the number of edges it contains. And if you look for a second, you'll notice that's actually not the shortest path from Lincoln to Rand. Right? If we wanted the path of minimum possible length, we should take a different route through this, Lincoln to MIT to BBN onto Rand, and that's only 3 edges, so that has a length of 3. And if you look a little more closely, you look at Lincoln and Rand, you'll notice there is no 2-edge path between them. You can just sort of try that out. And so, in fact, Lincoln, MIT, BBN to Rand is actually the shortest path between them. And so that defines a natural notion of distance on our graph. Right? We'll say that the distance between 2 nodes is the length of the shortest path from one to the other. And so, again, we have to remember that length here and distance really means in the number of hops that you take in the network. It's not a physical or geographic concept. And so in particular, Lincoln and Rand are pretty far apart. They're on opposite coasts of the US. But in the graph, they're at distance of 3. Right? In the same way that, say, Lincoln and Harvard are much closer to each other. Right? They're both in the northeast US. And yet, because they're on opposite sides of that 6-node ring, they too have a distance of 3. Right? So distance of 3 in the graph could be very different from distance in the physical world. Okay. There's one last definition that's useful to talk about, which is if a graph is not connected, then we'd like to understand the ways in which it breaks apart into separate pieces. Right? So imagine, for example, we have this 13-node internet, and we're thinking about the idea that links might fail, for example. And that's certainly something that you worry about when you build a communication network. Right? So a construction crew starts digging up a sidewalk to work on the water system, for example, and they might accidentally cut through some gigantic telecommunications cable and actually remove an edge from some communication network. Now, if you look at this 13-node internet, people were clearly thinking about that because you can try it out. If you were to destroy any one edge in this graph, the graph would actually still be connected. Right? There's always sort of another way to go. Right? Even across the country, there were these 2 ways. There's MIT to Utah and there's BBN to Rand. But of course, if you actually were to lose both of those long-haul links, for example, the graph would fall apart. And the 2 things it falls apart into we'll call connected components. Okay, so when a graph is not connected, we're going to talk about its components. And a component is a set of nodes with 2 important properties. One is that the set of nodes is internally connected. So if I were to look at it as just a graph in itself, it would be a connected graph. But it also has no edges to the rest of the graph. Right? So it's sort of as big as it can be in the sense of being connected. Everything else is somewhere else and is not linked by edges. Okay, so in this graph in particular, if I were to remove those 2 cross-country links, we would have a 6-node connected component on the East Coast and a 7-node connected component on the West Coast. So the idea will be to take these basic vocabulary items, right? The notions like path, connected, length, distance, component. We're going to take those, and those are going to be sort of our basic working ingredients for reasoning about graphs in this first pass on them. And so what we actually want to do next is think about how can we take these ideas and start thinking about graphs in a more abstract way, and in particular, to get leverage on graphs that may be too big and too complicated to simply draw and work out by hand.